All right, hello and welcome back to another Math 5 video. Today we're going over section 2.6, which is on function transformations, and is one of the sections that is covered in worksheet number 2. A lot of this information is very important for worksheet number 2 and beyond. So I strongly recommend that you watch this entire video, either all at once or in a couple different sittings. Okay, so there's going to be a lot of kind of prerequisite material here, stuff that either you should know or you're just going to be reminded of here. So I'll try to go quickly through it so that the video isn't too long. Okay, so we're going to start by looking at some of the basic functions that you need to know and that you need to know very well. So the first one is the identity function, which is just y equals f of x, or well, yeah, y equals x, or f of x equals x. This is a very simple function. The output is just the same as the input. So we can plug in a few numbers. You should be able to make a table for any of these functions. And the numbers that I generally plug in are -2, -1, 0, 1, and 2. Okay, so for the identity function, the output is the same thing as the input. It's just, y is equal to x. The y value, the output value, is the same as the x value, or the input value. Okay, so we should be able to graph this. -2, 2. You can see the graph is already done below, but if we had a piece of graph paper, we could just plot these points. And then it turns out that all of the points on this, for this function, lie on a straight line, and we put arrows on the end of it. A couple of facts. I won't read these facts for every one of these functions, but the domain is all real numbers. -infinity to +infinity. The range is all real numbers. This thing is symmetric about the origin, meaning if you were to rotate this 180 degrees, it would just land on itself. It's an increasing function from left to right. And then the end behavior is it goes down on the left and up on the right. Okay, so a line. And we don't want to spend too much time, I don't want to spend too much time talking about this basic function. We're going to transform this function. We're going to squeeze it, maybe flip it, or do different things like that. So we want to know this function very, very well and be able to graph it very quickly. Same thing with the absolute value function. The absolute value function, so we'll make a table for it, is pretty simple. You get an input, you take the absolute value of that input, and that's your function. Oops. Let's see if we can. So we'll do -2, -1, 0, 1, and 2. And then I'll, okay. So let me copy this. All right, so we're going to plug in -2, -1, 0, 1, and 2. And so here, f of -2 is just the absolute value of -2, which is 2. So that gives us an ordered pair, -2, 2. I'll plot it here with the black dot. F of 0 is the absolute value of 0, which is 0. So that gives us the ordered pair 0, 0. And then f of 2 is the absolute value of 2, which is just 2. And so that gives us the ordered pair 2, 2. And then the other ones are 1. So the way I remember how to graph this is the vertex of the absolute value function, absolute value of x, is just at 0, 0. And then we go over 1, up 1, over 1, up 1, and plot a point each time. We also do the same thing to the left 1, up 1, and then from there to the left 1, up 1. Or if you want to start at the origin, to the left 2, up 2, that'll get you another point. Knowing that basic shape will help you when we when we squeeze this thing, let's say we stretch it out by a factor of 2 in the y direction, in that case, you will go over 1, not up 1, but up 2, twice as much, because it's been stretched by a factor of 2. And so we'll get into that. So hopefully you've seen this function and you know it very well. It's basically 2 rays pointing outward. And if you take a look at the first ray that I drew, it's really just this x. The absolute value of x is just x when the x values are positive. And then really it's this negative portion over here. That negative portion, the absolute value makes it positive. So it would, that bottom portion of the line comes up, and that's how you get the absolute value function. Okay. The squaring function. This is probably one of the most popular functions, one I'm sure that you've worked with a lot. Let's take a look at that one. For this one, we'll plug in, let's say, -2, -1, 0, 1, and 2. And f of -2 is -2 in parentheses squared. -2 times -2 is +4. So we get 4, 1, 0, 1, and 4. And that quickly, we should have those numbers in our head, basically, so that we can just mentally graph it. 0, 0, to the right 1, up 1, and we plot a point, or to the right 2, up 2 squared, which is 4. Okay, so that's how I graph my parabolas. I plot the vertex and then left 1, up 1, and then from the vertex again, left 2, up 2. Thinking about it that way would be, might be good for when we start transforming these. The square root function is very similar. It is just half of a parabola on its side. So the numbers that we plug in for the square root function are a little bit more, you got to put a little bit more thought into them, because you can't take the square root and get an integer of any number. You have to choose very nice numbers. So I'll choose -1 just as an example, 0, 1, 4, 9, and that's about it. Okay, so -1, I put that one as an example to show that the function is undefined when x is equal to -1. Notice that over here at -1, I'm just going to put a dashed line. The function doesn't exist over there. The domain does not include -1. So we'll, just kind of forget about that. The square root function starts at 0. F of 0 is the square root of 0, and that is equal to 0. So we just take the square root of these numbers. 1 is the square root of, f of 1 is the square root of 1, which is 1. The square root of 4 is 2, and the square root of 9 is 3. And so I'll plot these points. It looks like they have most of these already on there. I'm going to plot them in red. 0, 0 is there. 1, 1. 4, 2. 1, 2, 3, 4, and 2. Yeah, and you see that they plotted 2 other points in this textbook example. But, you can memorize the square root of 2 if you like, or the square root of 3. The square root of 2 is approximately 1.4, and the square root of 3 is approximately 1.7. So you can see they've approximated those on there. But, so I'll teach you the way I do it. From the vertex of this square root function, you go up 1, up 1 to the right 1. That's how you get that first point after the vertex, and then up to over 4. Basically like the parabola, but on its side. Okay, so there we go. You can read about the domain range. We did that in a previous video. We talked about that in a previous video, and we talked about that in class already. I won't go over all of that. If you have questions on that stuff, feel free to bring that up. This video, I don't want it to be super long, so we'll move on there. So as I mentioned, we want to be able to graph these very quickly so that when we get more complex problems, those can be done fairly quickly as well. And I don't know if I mentioned this, but all of this is in the textbook. I've basically just taken parts of the textbook and put them here to talk about them. Okay, so the cubing function. Here we'll plug in -2, -1, 0, 1, and 2. And I'll just do one example. This cubing function cubes the input. So -2 cubed is just -2 times -2 times -2, which is -8. So -8, -1, 0, 1, and 8. So the shape of the cubing function, yeah, if you take a look at the graph, they've scaled it differently on the y-axis. They went by 2s, and then on the x-axis by 1s. Okay, so it's going to be 0, 0, then over 1, up 1. It looks like up 1/2, but it's actually 1 since it's scaled by 2. And then over 2, up 8. Okay. Now, this is an odd function, meaning it's also symmetric about the origin. So you do the same thing to the left. We go over 1 on the left side, and then down 1, and then over 2, down 8. And then you get 5 points that will pretty that will describe the function pretty well. Those 5 points are enough to graph this thing. Okay, so you can take a look at the information there about the cubing function. And then finally, the cube root function, I believe, is the last one that we'll point out in its most basic form. Let's see. Okay. So what should we plug in for this cube root function? Just like the square root function, we need to be a little bit careful and choose these numbers well, because we can't take the cube root in our head of any number. We need to choose numbers that are perfect cubes. So it'd be a good idea to choose actually the ones that are in the y column for the cube function. Those are definitely perfect cubes. So we'll choose -8, -1, 0, 1, and +8. And then I'll show one of them as an example. F of -8, that is just going to be the cube root of -8. But we know that the cube root of -8 is -2, because -2 cubed is -8. And so we can fill in the y side, -2, -1, 0, 1, and 2. So the cube root function, similar to the square root function, is basically just rotated, flipped on its side, the cubing function. In the case of the square root function, it's only half, because we can't have the other half of the parabola, otherwise it wouldn't be a function. In this case, we can have the whole cube function rotated on its side, because if we rotate the whole thing, it's still a function. We'll talk about that later in this class as well, about one-to-one functions. That's for another day, though. Okay, so we'll plot these. The basic shape here is, the origin, 0, 0. And then we go up 1 over 1, up 2 over 8, down 1 over 1, and down 2 over 8. We want to do this basic shape of the function, the basic shape, because we're going to stretch it, compress it, translate it, scale it. We'll do all sorts of things. All right, so let's take a look at a couple of examples here. We already know what this basic function looks like. The f of x equals the absolute value of x. And actually, to save a little bit of time, maybe I'll just copy the absolute value of x. right there. Oops. Okay. Now, what about the absolute value of x plus 1? G of x is defined to be the absolute value of x plus 1. So if we plug in -2, what will we get? -2 in absolute value plus 1. We still take the absolute value of -2 to get 2, and then we add 1 to that. We add 1 to that y value to get a new y value of 3. G of -1 is the absolute value of -1 plus 1. This is 1 plus 1. So we still get the absolute, we still get the value 1, but then we're adding 1 to it. And so we get 2. And so if you start to notice a pattern here among these two functions, you see that g of x is going to be the same value of f of x, but plus 1. So we're going to get 1 more there, 1 more there, and 1 more here. Okay. So what do you think h of x might be? What would these values be for h of x? H of x is defined to be the absolute value of x minus 3. So it's going to have the same values as f of x, the absolute value function, but minus 3. They're going to be 3 less. So let's go ahead and plug in 1 as an example. H of x, oops, h of -2 is the absolute value of -2 minus 3. That is 2 minus 3, which is -1. So -2, -1 is one of the points on the graph of h of x. Let's do one more. Let's do h of 1, let's say. H of 1, we're plugging in this x value, is going to be the absolute value of 1 minus 3. The absolute value of 1 is just 1 minus 3 is just -2. Okay, and then we can plug in the rest of these x values. I won't walk through all of that, but they will be -2, -3, and -1. Okay, so now I will plot these, and so we can see how these functions are related. If we know this absolute value function really well, we should be able to graph g of x and h of x very quickly. Okay. So let's take a look. And okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is the x axis. This is, I'll call it the y axis, and then we'll copy this just to make sure we have one handy. Okay. Okay, so let's go ahead and plot. I'll plot all 3 of these functions. The absolute value function. Oh. I just thought of something, but to make this graphing a little nicer, we'll do it on the next one. Okay, so it looks something like this. That's the absolute value function that we graphed before. Now plotting just the points, -2, +3, 1, 2, 3, -1, +2, looks right here, 0, 1, 1, 2 and 2 comma 3, we get this blue graph here. And so how do these two compare? The y values of this function g of x, these y values are one larger, so you would expect along the y-axis for it to be 1 unit higher. And that's exactly what we get. The blue graph is 1 unit above the black graph. Now let's take a look at the red one. We had h of x is the absolute value of x minus 3. So I will write that here just to point out one thing. The h of x is the absolute value of x minus 3. So h of x is really f of x minus 3, right? F of x is the absolute value of x. So it's just f of x, 3 units, but 3 units less. Let me plot these in red. And just to point out here, it might be hard to see what I'm trying to plot here. I'm plotting these x values with their corresponding y value in this column here for this red graph. Okay, so -2, -1. Oh, that's a highlighter. -2, oops, -1. -1, -2. 0, -3. 1, -2. And 2, -1. So if we graph that, oops, it looks something like this. These are just sketches, but how do these compare? If you look at two corresponding points, it's just the function f of x in black, but the red one is 3 units lower. Okay, so you can see here in this green box, we have it, worded a little more technically. If k is a positive number, and any function whose graph is determined by f of x, the graph y equals f of x plus k is going to be just f of x shifted k units upward. And then if y is defined as a function f of x minus k, that's exactly what h of x is. H of x is f of x minus 3. Then this green box tells us that it's going to be the graph of f of x, the black absolute value function, shifted downward k units. Okay, I hope that is clear. These examples take a long time, just to kind of plug in the numbers, but yeah, hopefully that's pretty clear. Okay, yeah, you saw that coming, hopefully. All right, we're going to have a lot of transformations. This one is shifting, also called a translation. So vertical translations, that's vertically shifting. That's one of them. I think there's going to be about 6 that we're going to go over, or maybe 3, but there's horizontal translations, which are also translations, but we consider vertical and horizontal separately because they're denoted a little bit differently. They're written differently. Excuse me. Okay, so let's take a look at f of x equals x squared next. And we'll copy this. This is one of the ones that, sometimes gives students a little bit of trouble. Let's see, and we'll copy this thing. So let's see if we can write this down and make sense of it. I almost thought of leaving off the words horizontal translations to kind of leave it more as a surprise, but there it is. Okay, let's see. Okay, so let's take a look here at g of x now. G of x, we'll do it in blue. G of x is equal to x plus 2. And so that we see what kind of transformation takes place here, I'm going to choose, actually, let's go ahead and plug in -2, -1. Let's plug those in. -2, -2 plus 2 squared. That's 0 squared, or 0. So we'll put a 0 here. G of -1. This is -1 plus 2 squared. That's 1 squared, which is 1. G of 0 is equal to 0 plus 2 squared, which is 2 squared, or 4. G of 1 is 1 plus 2 squared, which is 3 squared, or 9. Let me write a couple of these in. 1, 4, 9. And G of 2 is equal to 2 plus 2 squared. 4 squared is 16. So we've got a 16 here. So how are these two functions related? Let me plot all of the points that I can. And remember that we're using these as x values and these as the y values for g. Okay, so -2, 0. -2, 0 is here. -1, comma 1. 0, comma 4. And then 1, comma 9 isn't really going to fit on here. It'll be somewhere up here. But notice what we get. We've got half of the parabola. Okay, so maybe we need to plug in a couple of other values for x. Let's go ahead and try plugging in -3 and -4. G of -3, I'll do this one in my head here. G of -3 is -3 plus 1 is -1. We square that and we get +1. And then -4, G of -4 is -4 plus 2 squared. That's -2 squared, which is 4. Okay, so -3, 1, 2, 3, +1, that point goes there, and -4, 1, 2, 3, 4 goes there. Okay, so we get the other half of the parabola. And so what I wanted to see is, how do these two functions relate? How are these two related? Well, we see it says horizontal translations there on the page. It looks like every one of these points on the original graph got shifted over 2 units to the left. And so f of x equals x squared, and g of x equals x plus 2 squared. This plus 2 here made our function shift left 2 units. Now, a lot of times students get confused because they say, well, it's a +2, so they expect it to go to the right 2 units, in the positive direction 2 units, but it actually goes in the negative direction. The reason for that is because, let's just compare 2 of these points here. The point 2, comma 4 for the original function. Where is that y value of 4 going to occur? And let me put a red x in it here. 2, comma 4 is that point there with that x. That was produced by f of 2, 2, 4. So where is that same y value of 4 going to occur for g? Where are we going to get a 4 for g of x? Well, we don't need to plug in 2 as our x value, but we could just plug in 0 because my x value is going to be increased by 2 in the g of x function. So notice if I plug in 0, the value that's getting squared is still 2, which is going to give me 4. So 0, 2 units earlier, I'm going to get a y value of 4. And you can see how that creates that horizontal shift to the left 2 units. So the +2 will increase my input value by 2, and therefore the same output values will occur 2 units earlier, or 2 units to the left. Now, that's a lot of kind of stuff there, but we can generalize this and say, let's start with, let's start here. Let's say we're given some value h, which is a positive number, and we have a graph y equals f of x, which in this case, f of x was x squared. The graph y equals f of x plus some value h inside of the function is going to be just the graph of f of x, but shifted to the left h units. Okay, and that's exactly what we saw here with the 2 unit shift to the left. All right. Now, what about the graph of y equals f of x minus h? You can probably guess this one. If we subtract the value, that's going to shift to the right h units. And so again, this is why it's really good to know the function x squared really well. So then we can graph a transformation of it. It has the same shape. Notice if you know that the vertex is going to be, I'll use x as the same, 2 units to the left, then I just go over 1, up 1, over 2, up 4, left 1, up 1, and left 2, up 4, and I have a basic graph for g of x very quickly. Okay. All right, so let's go ahead and do another example here. And here we have this absolute value of x minus 2 and the square root of x plus 3. So let's go ahead and take a look at those functions. Oops, wrong tool. Delete this, copy this. And the square root function also. And so you can see, if we have these functions in our head, we know them very well, then all we have to do is say, okay, let me remind myself that x minus 2, since the minus 2 is inside of the absolute value, that's going to be a horizontal shift 2 units to the right. And so that means my vertex is now going to be at, not at 0, 0, but 2 units to the right of that. And then I go right 1, up 1, right 2, up 2. From the vertex, left 1, up 1, and from the vertex, left 2, up 2. And I've graphed. Notice I didn't do any calculation there. And again, if I knew the function in my head, I don't even have to graph the basic one. Okay, on the same little piece of paper here, or the same little graph, I'll graph the square root of x plus 3. And of course, I put that function, the square root of x, there as a reference, but it should be in your head basically. And so I know that the square root function starts at 0, 0. So now because of the square root of x plus 3, it's going to start 3 units to the left. So I'm going to start here. And my basic shape was up 1 to the right 1 from the vertex. Again, from the vertex, up 2 to the right 4. And then if I wanted to go up 3, 1, 2, 3, I just go to the right. Up 3 to the right 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a little bit off the page, but not a big deal. Okay. Looks something like that. And if I had graphed it 1, 2, 3 here, you would see the relationship really 1, 2, 3 clearly. 1, 2, 3. Every one of these points on this graph is just shifted to the left 3 units. Okay. And then we should put an arrow on the end of it to indicate it keeps going. All right. So very quick, no calculation. I went through a lot of calculations with some of these just to show like, okay, well, yeah, you can plug in a bunch of numbers if you want to and get your graphs that way. But once you're comfortable with it, you can just slide the graph over. Okay, vertical reflections for y equals x squared. Let's go ahead and get our x squared function. Okay, have it there. And then let's grab our table. So what does this negative do? If I define a function, let's call it g of x equals negative x squared, where f of x is equal to x squared. Notice what we get here. G of x is really just negative 1 times x squared, which is negative 1 times f of x. I just put a negative in front of the original function. And that's going to make all the y values just opposite what they were before. We'll plug in one number, g of negative 2. So we can see it's negative, or the opposite of negative 2 squared. The negative on the outside is not being squared, just the x value is being squared. And so this is the opposite of negative 2 squared is 4. And so that gives us negative 4. And so you can see that value of negative 4. I'm going to plot this point. Negative 2, 1, 2, 3, 4, negative 4 right there. And you can maybe already see the pattern. All of these are just going to be flipped or made opposite. And so we can plot all of these points. So how would you describe the relationship between the blue graph and the green graph? It looks like it's just reflected about the x-axis. Okay, that's a vertical reflection. For any function, y equals f of x, the graph of y equals negative f of x, or the opposite of f of x, is the graph of f of x reflected across the x-axis. Okay, so if you ever see, if you see this function, g of x equals negative square root of x, you should be able to graph that in 10 seconds. All right, very good. Horizontal reflections. What if we were to put the negative inside of the square root of x, or inside of the square root function? Just like earlier when we put the +2 or -2 inside of the absolute value or square, or whatever kind of function it was, it shifted it horizontally. The same thing is going to happen here. If the negative goes inside of the function, the reflection will be horizontal, meaning it will be a reflection about the y-axis rather than the x-axis. All right, so let's take a look at this square root function here. Let's see, is this going to... No, that's not going to work for us because this is a square root function. Let's go ahead and go up and grab that. The square root function. And this. And so this is actually a very good graph to use as an example, because the square root of x, the basic f of x here, its domain is all numbers larger than or equal to 0. But when we put this negative in front of there, let's take a look actually. Let's try to find g of 1. Right, just we have a 1 here as an x value. Let's plug that in. We plugged it into f and we got 1 out of that. But if we plug it into g, let's see, g of 1 is equal to the square root of the opposite of, and I plug in my 1. Now this becomes the square root of -1, which is undefined. or it's not a real number. In this case, so we'll just call it undefined. We're not working with imaginary numbers in this class. Let's try g of 4. But notice that this negative inside of the square root function is going to make any positive number I plug in, like 4, it's going to make it now the square root of a negative, which is undefined. Same thing with 9. So what can we do here? It doesn't seem like we can plug in any positive number. We can plug in 0. The opposite of 0 is just 0. So the square root of 0, that's 0. That one works. Let's try plugging in this negative value, negative 1. And you can probably see that, wait a minute, if you plug in a negative, that negative that's inside of the square root is now going to cancel out the negative. These two negatives cancel, and we get the square root of 1, which is just 1. So g of x is defined for negative x values. Because of the negative inside of the function, it will negate the negative of the x values, and therefore, you'll be able to take the square root. So the values that we should plug in for g of x, let's go ahead and choose a couple of values. How about negative 4 and negative 9? Let's see if those work. G of negative 4. Well, the square root of the opposite of negative 4. The opposite of negative 4 is 4, and so that is 2. Now we do get an output value. Put it in the wrong column. And g of negative 9. G is defined for an x value of negative 9 because the double negative gives us a square root of 9, which is 3. And so now we have, 4 ordered pairs that we can plug in. And just as a reminder, I'm using these x values with these y values here. Okay. So negative 1, 1, 0, 0, negative 4, 1, 2, 3, 4, 1, 2. And then negative 9, I can't graph that, but that's okay. This is enough. All right. And you can see this is a mirror image across the y-axis. Okay, so kind of cool there. You could plug in a bunch of numbers, but if you just remember, hey, if I see a negative on the x, on the variable inside of the function, then that's going to be a reflection about the y-axis. And then you don't have to plug in a bunch of numbers. I'm doing this work here on this one here, but in class, I'm just going to do them really quick. Not plug in a bunch of numbers. Okay, so here we have it. For any function f of x, the graph y equals f of negative x is the graph of f of x reflected across the y-axis. Notice the difference there, though. It's somewhat subtle. So for y equals f of x, y equals f of negative x, we said is, reflected across the y-axis. Let's see, how can I do this? Y-axis. But y equals negative f of x, this is the one that we went over previously, is a reflection, I'm just abbreviating that, across the x-axis. So you need to be able to, distinguish those two. And so in terms of the square root function, it would look like this. Oops. And like this. Reflection about the y-axis, reflection about the x-axis. All right. Oh, there's a lot of information here. All right. What if we put a number in front of the x squared, in front of the x squared function? Let's go ahead and take a look at that one. X squared. This one here. I'll do that. And what would that do to our graph? And I'm actually going to use, let's see. Can I use 1/3? I'm going to use, yeah, I guess 1/3 will work. 3 and 1/3, sure. So let's graph this in green. We already know what f of x looks like. It's right there. G of x is 3x squared. And so notice all it is g of x is 3 times x squared, but x squared is what we're calling f of x. And so we just have a number multiplying the function. The function f of x represents the y values. And so we're just going to multiply all of the y values by 3. That's actually all it is. I'll plug in one number so we can see g of -2. This is 3 times -2 squared. And you see that we're still going to get -2 squared, which is 4. That was the original function for f of x. And then we multiply by 3 and we get 12. Okay, so all I'm going to do is just multiply these y values for f of x by 3. So 1 times 3, 0 times 3, 1 times 3, and 4 times 3. So what about if we were to plug in or put a 1/3 for h of x? I'll do that in blue. H of x is equal to 1/3 x squared. It's just going to be 1/3 of the y value of f of x. So if we plug in, let's do h of -2, 1/3 of -2 squared, that's going to be 1/3 times 4, which is 4/3, which is 1 and 1/3. I'll do one more. H of -1 is 1/3 times -1 squared. -1 squared is 1. So this is just 1/3. So we get 1 and 1/3, 1/3, 0, 1/3, and 1 and 1/3. Parabolas have what's called an axis of symmetry. So about this axis here, in this case, the vertical line that goes through the vertex, this function will be symmetric about it. Okay, so let's go ahead and plot these. I'll do this in green for the g of x. -2, 12 is going to be off the page, but -1, 1, 2, 3 is not. 0, 0 is still one of the points, and +1. So what we call this, and I want to try to make it rounded here if I can, at the vertex, is imagine the blue graph getting stretched vertically. So all of the y values, they don't get shifted up by 2 units. They get multiplied by a factor of 3. So they got tripled because of that 3. Okay. And then in blue, I will graph the other. -2, 1 and 1/3 would be somewhere right here. -1, 1/3, 0, 0, 1, 1/3, and 2, 1 and 1/3. Looks like this. And so again, how do the blue graph that I drew and the blue graph that was already on there compare? It got squeezed down or compressed. It got divided by a factor of 3. Okay. So yeah, you can take a look at these 2 points here. the y values, it used to be 1, and now it's a third its size. All right, so I got, you can stretch or compress. So what values stretch, make it go up quicker? The values that will stretch the function are values that are larger than 1. So stretch, I'll just use a. If a is larger than 1, it will stretch it. If a is equal to 1, it just stays the same, because multiplying x squared by 1 is just going to stay x squared. And then squeezing it or compressing it will be the values between 0 and 1, like 1/2. It will cut it down to half its size, or a third, or any fraction or any number between 0 and 1. Now, of course, we can also look at negative numbers. We will also stretch if the value of a is less than -1, so like -2, -3, it would have stretched it, but it would have also flipped it, because we know if we multiply by a negative, we learned previously that a negative will flip it. So I didn't cover any negatives there, but the -3 will just stretch it by a factor of 3 and flip it. It does both. If we use a -1, then that would just flip it. That's what we learned on the previous 2 slides. And then we could also squeeze the function and flip it if the a value was between -1 and 0. So a fraction or some sort of number between -1 and 0. Okay, so they word it here very technically in this green box in the textbook. So if you put an a times the function, it will stretch vertically if a is larger than 1, or if the absolute value of a is larger than 1, meaning, in magnitude, it's larger than 1. Or it will be compressed vertically if the number is between 0 and 1, or if it is between 0 and -1. Okay. All right, so hopefully that helps a little bit. And the last one, they actually don't cover in the textbook, stretching, or at least not in section 2.6. I looked through the entire section, didn't find an example of it. So I'll just write up a page here for it. And it is for stretching or compressing horizontally. Okay, so I'll just say horizontal. I'm sure it's somewhere in the textbook, but they didn't cover it there, because they do cover it later in the textbook. Okay, so let's take a look at the example of, let's see, the x, f of x equals, and which one would be the best one to use? I will use the square root of x. And then I'll use f of x equals 1/2. Let's do the square root of 1/2 x. And we'll also look at g of x equals the square root of 2x. So what do you think this 1/2 will do? Feel free to pause the video and think about it. What is this going to do? What does the 1/2 do? What did the 1/2 or 1/3 do in the previous one? That would compress it. What is the 1/2 going to do here? Let's take a look. So we have now mastered the square root function. So we can draw a table for it really easily. Now this one here, we have to be a little careful on what values we choose. We said 0, 1, 4, and 9 were good values to choose. Let's make sure I'm using all the space. And the y values were 0, 1, 2, and 3. Let's make, and excuse me here, let me change these letters just to make sure, this is g of x, and we'll call this one h of x. And so I'm actually going to use different values of x for g of x, and we'll see why in a moment. The input is x, but in the function g, we're going to take half of that number. And so then we're going to take the square root. We want the number that we end up with under the square root to be a perfect square. So I'm going to use values of x that are twice as large as a perfect square, so that when I half them, we get a perfect square, and we can take the square root of it. Okay, so I'll choose instead 0, 2, 8, and 18. I just doubled these numbers here. And just a little bit of thinking ahead. So g of 0 is equal to the square root of 1/2 times 0. This is the square root of 1/2 times 0 is 0, and so that's 0. G of 2 is equal to the square root of 1/2 times 2. When we half 2, we get 1. The square root of 1 is 1. G of 8, we take half of 8, resulting in 4 under the square root. The square root of 4 is 2. And the last one, g of 18, is equal to the square root of half of 18. Half of 18 is 9, and its square root is 3. So we get 3 here. Now let's take a look at what that graph looks like before we do the next one. Let's go ahead and take a look at the graph. That's the square root of x. Okay, and so the points, I'll graph whatever I can. In blue, they are 0, 0, 2, 1, 8, 2. I'll try to do that one. 1, 2, 3, 4, 5. 6, 7, 8. Somewhere right there, and then a y value of 2. So what did this do? It stretched my function by a factor of 2. It stretched horizontally. And that's what it looks like. This is we want to describe it as a horizontal shift. And actually, I would like to show a little quick example here. Oh, do I not have that? I had it earlier and then I restarted my computer. So let's take a look. See if I can pull it up quickly. Just to see, so here's a regular function called sine of x. And if we look at sine of ax, where we put a number in front of there, you can see that it stretches. Right now it's stretching the function. So here's a value. Whoa, that's very stretched. Here's a value that's between 0 and 1, and it's very stretched. And notice how it's coming back to its original shape. Once it gets larger than 1, it actually starts to compress it. This value getting larger and larger, it's compressing the function more. So we can see that values that we have inside of the function that are larger than 1 are going to compress the function horizontally. Okay, so let's jump back over here. So yeah, this is a stretch of a factor of 2. And then we'll take a look at h of x as our last example for this. So if you were thinking maybe it was going to compress, because I tried to trick you here and I said that this 1/3 compressed vertically, the 1/2 inside of the function actually stretched it horizontally. It did the opposite, which is not too different than what happened when we had a minus sign over here, or a plus sign went left. It kind of did the opposite of what we thought was going to happen. Went to the left 2. So the 1/2 inside of the function stretched it by a factor of 2. Okay, so we need to kind of pick these things up and be familiar with them. And let's see what we haven't used green, so I'll use green. So here, what kind of x values would be good to choose? It would be good to choose values that are half of a perfect square. That way, when we double them inside the function, we get a perfect square value. So half, so 0, 1/2, 2 is half of 4, and then 9/2, which is 4.5. Okay, so let's go ahead and graph this one. And so just something to notice really quickly, I'm going to do h of 2 first. H of 2, notice if I use the x value of 2, I get the square root of 2 times 2. I double the x and get 4. The square root of 4 is 2. So notice how I get this y value of 2 occurs when x is 2. Whereas before, the y value of 2 would occur when x was equal to 4. So notice it occurs in half of the time, in terms of x, because I'm doubling the x value inside of the function. So my y values occur half the time, earlier, if that makes sense. So let's go ahead and plot that point. 2, 2, 1, 2, up 2. Here we go. And so notice these 2 points, I'll mark them with a red X, correspond to each other. It just occurred half as quickly, or twice as quickly, however you want to call that. And then let's go ahead and do the others. H of 1/2, an x value of 1/2 is now going to give me the square root of 2 times 1/2, which is the square root of 1, or just 1. And so I get 1/2 comma 1. Again, you can see that. I'll mark it with another red X. That one also occurred in half the time. Instead of getting a y value of 1 at x equals 1, we got it at half of 1, or 1/2. Instead of getting a y value of 2 at x equals 4, it occurred in half the time at x equals 2, because we're doubling the input. Hopefully that makes sense. It's kind of cool, I guess. The square root of 2 times 0, that's going to be the square root of 0. This point here, actually this point here also occurs in half the time, but half of 0 is still 0. And then h of 9/2 is equal to the square root of 2 times 9/2. This is the 2's cancel. This is the square root of 9, which is 3. And that one, actually that one will fit, because 4.5 comma 3 is right here. And so there we go. Looks something like this. What happened here? We compressed. We cut it down to half its size in the x direction. Okay, so all right. So how's another way to read this in case we want to quickly graph these functions? Let me put these 0, 1, 2, and 3. If we know the table of the square root of x very well, then this horizontal stretch or compression, what it's actually doing is the y values, if we want them to stay exactly the same, those are exactly the same as long as you get the x values of the original function and just cut them in half. Divide them by a. A is a value of 2 in h of x, so we just divide everything by 2. In g of x, a is 1/2. If we divide all of the original x values by 1/2, what it will do is it will double them. Okay, so hopefully you can see that. Um, so if you know that it's a horizontal stretch or compression, then you can just adjust the X values by cutting them in half or doing something like that. Okay, so that's that one. And I think we're almost done. Oh, I don't want to, this has gone on pretty long. So let's sketch these graphs real quick and we'll be done. Just to show how fast these can be done now that we have, and then the cube root, let's see if we can, oh, we didn't really even talk about the cube root too much, which is good because we can show just by knowing this, all we know is the basic cube root function. We can quickly graph any other cube root. Okay, so what do we do? Okay, I'm going to draw the vertex. So the first one is the original parent function is how it's called. The parent is just the basic one. It's at 0, 0, right? We know that this positive 2 is going to shift 2 units to the left. I'll put an X here. That's where the new vertex is now. This negative is going to reflect the function across the across the X axis. So it's going to be opening downward now. And then this plus 3 is going to shift the graph up 3 units. So this is where our new vertex will be. And then if we know the shape, to the left 1, down 1, from the vertex to the left 2, down 4, right there. And then same thing on the right side. Bam. That's how quickly we can draw this function, which, I would say this is, somewhat complicated of a function. It's not that simple, not as simple as x squared, but it basically is as simple as x squared if we know x squared really well and we know these function transformations. Okay, so that was pretty fast. Not a single calculation done. Okay, same thing for the next one. I'll graph it in blue. H of x is, some transformation of the cube root function. Okay, so the -2 makes me go from the origin to the left 2 units. This 2 tells me it's going to stretch by a factor of 2 in the y direction. So I'm going to double everything in the y direction. And then I'm going to move down 1 unit. So I'm going to go down 1 unit and start there. So I'll start here. Let's go ahead and do that. Usually I go up 1 and to the right 1. But since that factor of 2 is stretching everything in the y direction by a factor of 2, I'm going to go up 2 twice as far and still over 1. Right? Normally it would be right here, but I'm stretching by a factor of 2, doubling in the y direction. Okay. Then I would have normally gone up 2. And how can I, let's see, I think there's a little laser pointer. Yeah, so up 2 and then over 8. 1, 2, 3, 4, 5, 6, 7. And actually, oops, let me make sure. Okay, let me start over here just because of the scaling. I forgot the scaling is different on the X and Y axis. So yeah, let's start over here. And so far I've only shifted. And did I go the wrong direction? Yes, I did. The -2 inside of the function is to the right 2 units. Hopefully you were thinking that. So good thing I caught it there. Yeah, we need to go the opposite because it's inside the function. So my starting point is actually going to be to the right 2 and down 1 right here. And then the original function is up 1 to the right 1. So I'm going to plot that. And I'm using the scaling here on the x-axis. The scale goes by 2 in the x direction. So up 2 over 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then down 1 over 1. Down 2. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these, no, I'll just graph it. Let me do that. This is how the function would look if there was no factor of 2 scaling this thing. I'll highlight that factor of 2. But since there is, I just need to stretch this every y value. Instead of going up 1 unit, I'll graph it in green, it's going to go up twice as 4. I'm still getting used to these new controls in this app. So this origin point stays the same. Everything else gets stretched by a factor of 2 from there. So we'll be down here, this point here. 1, 2, 3, 4. So go down here. And 1, 2, 3, 4. Okay. Does this look like it's stretched by a factor of 2? Yes. Okay, it's stretched vertically. All right. And yeah, let me pause for a moment. All right, let's go ahead and continue here. We'll just finish this off. So this is just an example of how the transformations can be applied to basically any function, and they look very similar. So if we look at the function here, is this the same one? No, they're a little different. So the transformations will appear very similar. So you should be able to recognize if you look at something like this, we want to read this from the inside out using like the order of operations, starting with the x. So let's say I plugged in a number into this function here, -2 times, let's say 5 minus 3 squared plus 1. What would you do first here? Using the order of operations, you would do what's inside the parentheses. You would combine with this -3. So that's why we should then say, okay, well, and this is going to shift 3 units. And this is going to be, let me make sure I got it right, to the right. Right? 3 units to the right. Okay, once we do that, okay, you'd square it. That's just what the function does. So you'd square and get 4. Then what would you do next? You should, according to the operation, the order of operations is multiply it by that -2. And so that's going to do 2 things. That's going to stretch vertically by a factor of 2. And then that's what a 2 does. It stretches the function by a factor of 2. The negative will also reflect about the x-axis. Okay, so make sure to read that at the same time. Stretch, reflect, or reflect and stretch, whichever one you want to do first. And then finally, once you do that, and notice what happens to the 4. The 4 gets doubled and made negative. And then the +1, that's going to shift it up 1 unit. Okay, so you should be able to read this in any of these functions. They all have the same transformations, and then here they kind of make it more generic. They put an f function there. It's just that's how it would look in general for any function. Okay, and so here they kind of list what inside of the function, so whether it's an absolute value function or a square function, square root function, cube root, that plus or minus h is shifting horizontally, and it says the opposite direction of sine. That's a pretty nice note that they put there. Then outside of that, we have vertical reflections if there's a negative, and a vertical stretch or compression, depending on the value of A. And then finally, the value on the outside, plus or minus K, shifts it up or down K units. Okay, cool. And we're almost done here. So let's graph a couple things here. This is very similar to what you'll see on the worksheet. So I'll do this, maybe I'll do a couple of these. So let's just do this problem. This is example 9 of the textbook. Given the graph of f of x, graph g of x, which is the opposite of f of x plus 1 minus 2. So all I'm going to do is shift 1 unit left, reflect about the x-axis, and then shift 2 units down. Okay, and so we can just do that in the picture. I'm gonna start with this point here, move it 1 unit to the left, reflect about the x-axis, so that would make it, put it over here, and then shift 2 units down. Here's our point. Okay, next point, I'll do a different color. Shift 1 unit left. Reflect about the x-axis. If it's on the x-axis, it just stays there when you reflect. And then shift 2 units down. Let's put that there. Okay, next, we'll do one in blue. The one at the origin, shift 1 unit to the left. Reflect about the x-axis, it just stays there. And then shift 2 units down. That's what we get. Another one in red, 1 unit left. Reflect about the x-axis. Instead of being 3 units below the x-axis, it will be 3 units above the x-axis, and then shift it 2 units down right here. Oof. And finally, the last one here, 1 unit left. Reflect about the x-axis and 2 units down right there. So now let's see, the shape of our graph should be pretty much preserved except for reflection. You know, it's a reflection. It's shifted, flipped, shifted. So the shape should be very similar to what it was originally. We'll graph it in blue. It's going to look like this. Very carefully graph that. Yeah, it looks like it's upside down, to the left 1 unit, and down 2 units. Cool. Perfect. Okay, so now actually something else I want to show is how do we get the coordinates of all of these points? That would be a good exercise as well, and I haven't really talked about that very much, so hopefully everybody's still watching the video and will pay close attention to this part. Because, yeah, this is going to be a good exercise here. So the points that are on the original graph are 1, 2, 3, 4, -4, 0, -2, 3, 0, 0, 2, -3, and 1, 2, 3, 4, 4, 0. Okay, this. So here's what you would get, or here's how to tell what the x and y values are if you have just for a certain transformation. Let's say x and f of x plus 1. If we shifted this thing, look at for this transformation, 1 unit to the left, that would just change my x values and they would all decrease by 1. So the y values would stay the same. And all of the x values would decrease by 1. -5, -3, -1, 1, and 3. And notice I'm actually going to mark them in blue, it looks like. And I'll put dots here in blue. I've actually already put x's in their places. Notice right here, -5, -3, comma 3, -1, comma 0, 1, comma -3, and 3, 0. So I want to show, how you can draw the table for these, where, if you know that it's going to be a horizontal reflection, or sorry, horizontal translation, then that just decreases the x value by 1 in terms of the table. What does the reflection do? That reflection about the x-axis, since it's a negative outside of the function, it's multiplying the function value by a negative. What that's going to do is, well, let's see, you can pause the video and think about it. X negative f of x plus 1. How does that compare to the values above? That is only going to change the y values. I'll graph this in black. The x values are all going to stay the same. When you reflect something, you flip it. If you flip something like this, the x is not changing, just the y. The y's are changing to their opposites. So the x's would stay exactly the same. All of the y values would now flip. So that'd be 0, -3, 0, +3, and 0. I'm just changing the y values from up above. And so let me graph these new points. I'll graph them in black. -5, 0. Notice that anything on the x-axis will stay there. -3, -3. There it is. -1, 0. 1, 3. 1, 2, 3. And 3, 0. So notice how the black graph and the blue graph compare. They're just reflections of each other about the x-axis. The blue graph that I just graphed, not the answer one. And then finally, the last one here is -2. We'll do that one in red. That's going to be just the rest of, so negative f of x plus 1 -2. What does that -2 affect? Does it affect the x values or the y values? It affects the y values. The things that affect the x values are going to be, when you have something inside of the function like f of 2x, like the square root of 2x, that's horizontal. Or f of -x, the square root of -x. When it's inside of the function, these affect the x values. So since this -2 is outside of the function, it's going to affect the y values, and it's just going to decrease them by 2. So if we look at these y values here and just subtract 2 from them, -2, -5, -2, 1, and -2. All right, so that's -5, -2, -3, -5, -1, -2, 1, 1, and 3, -2. Yeah, that's the answer that we got. I might say, oh, that's kind of lame, or what are we doing that for? It is very important that you understand both what happens graphically, and really this graph, every graph has a table, that corresponds to it that you can write out. So it may be beneficial to know that as well. I think that comes up a little bit on the worksheet. Okay. Yes. All right. So, and I'll quickly pull up the worksheet. Let me pull it up just to kind of point out which problem I'm talking about, or problems. Worksheet number 2. We don't want to show the answers just yet. Yeah, of course, yeah, all of these, you should be able to look at this and say, that's the square root function reflected about the y-axis and shifted up 1 unit. So we graphed it. There you go. One for free. This one right here, though, is a little bit trickier, maybe a little bit. And you're just given 3 points. You can write down a table that has those 3 points, and then ask yourself, what would this 2x do to those coordinates? And I'll tell you, well, we've already looked at one like this. It will, if there's a 2x inside the function, did we do 2x? Yes, we did. How does this table compare to this original table? The 2x made the x values, get cut in half. It's a horizontal stretching, and so we can just write down all of the coordinates of those points, cut the x values in half, leave the y values exactly the same. Notice the y values are identical. Cut the x values in half, and that's the new graph. Okay, so very simple if you understand what's going on. All right. If you know everything, it's very easy. All right. Let's we'll do this last one. This is just for fun now. All right, so this is an absolute value function, but it's also flipped upside down. So we know we should have a negative there. What else? What else do we see about this? The usual absolute value starts at the origin. So this one starts 2 units higher and 1 unit to the right. So actually take a second here, see if you can graph the function, pause the video. Oh, sorry. See if you can write the equation of the function. Maybe you can do it yourself before I write it down. And then I'll do it. So 2 units up is going to be a +2. 1 unit to the right, if I can remember this correctly, hopefully I don't make a mistake again. 1 unit to the right is like that. And then the absolute value is usually over 1, up 1, and there's a point. Over 1, up 1, and there's another point, and the same thing in the negative direction. But this one is not like that. This one's looks like it's very stretched, and they actually put 3 big solid points for you to see. So you have to go over 1, 2, 3, 4, up 2. Okay. And you can actually also see, if you look closely, maybe I can erase that. You can also go over 2, up 1. So when you go over 2, and you go down 1, that's different than the original graph, because when you would go over 2 on the original graph, you'd go up 2. So it looks like instead of going over 2, up 2, you're going over 2, up 1. You're going up, or over 2, down 1. That's half as much as it would normally. It would look something like this if we had just shifted and reflected. But it looks like it's also been scaled. It's been compressed vertically to half of its speed. Okay, and then we can also see this by, let me use, if we go over 1, how much do we go up here to get to this next point? Over 1, I keep saying up, but it's down because it's flipped. But it's over 1, down a half. So yes, there should be a 1/2. So this is negative 1/2. Absolute value of x minus 1 plus 2. That is the equation of this graph. Okay, it crosses at 5. And actually, there's an easy way to check. Let's plug in 5. Let's call this f of x. So notice this big green point here, f of 5 should be 0. So f of 5 is negative 1/2 times the absolute value of 5 minus 1 plus 2. This is negative 1/2. The absolute value of 4 is 4. I'll just write that out. Plus 2. Negative 1/2 times 4 is negative 2. Plus 2 is 0. That checks out. I'll check this one as well. F of negative 3 is negative 1/2. Absolute value of negative 3 minus 1 plus 2. We can see that we get an absolute value of negative 4. That's going to end up being 4 times negative 1/2 is negative 2 plus 2 is 0. So that's good. Yeah, it looks like this thing checks out. Cool. And notice we didn't do any calculation to actually get that equation there. Just looking at the shape of the graph, how it's flipped upside down, its vertex is 2 units higher and 1 unit to the right of where it normally is, and that's all. You know, I wrote a few steps here with just to kind of show my thinking, but you know, doesn't take too much time at all. All right. Oh my gosh. Well, yeah, we'll skip this. We're not going to do this example. This video is long enough. All right. So hopefully you enjoyed that. And leave a like on the video or a comment, you know, putting, you know, whether you like the videos or not or whatever. If you have any comments, feel free to put that. I'd be happy to read them. All right. So I'll see you next time. Bye for now.